So this is some work I have been working kind of on my side, and it's about trying to get more dynamical insights from surface drifter observations. It's actually semantically very related to Alexa Grisso's talk and Julia's poster on the first day. But this is a collaboration with people outside TR. It started way before I came. Okay, so yeah, we are looking at surface drifter data, and there are some very nice surface drifter program data, and it's all publicly available, and they do all the data engineering for us already, that they do all the denoising and stuff. And there are more than 100 drifters, like in one of the campaigns, they have a few thousand drifters. And another very nice thing is that they have a winter campaign and a summer campaign, so you can see some seasonality there. Just to decrease my chance of losing all the atmospheric people immediately from this slide on, I want to mention that this is kind of like all the methodologies in this work, they in principle apply to all the Lagrangian observations. So they in principle can be applied to atmospheric balloon experiments. I just didn't come across such data yet. Okay, so this is how the data set look like. This is the Gulf of Mexico, and this is a video of the drifter locations in time. And the left is the GLAD campaign in summer, and the right is the laser campaign in winter. And you can see that very clearly that there is this multi-scale motion that's resolved in the drifter data set. So you see this anti-clockwise, clockwise rotations that's clearly an imprint of near inertial waves. And there are also these large-scale motions, which are probably due to balance flows. And you can also see that they have very good spatial coverage. So like in terms of pair separation statistics, they can cover the spatial range from like 10 meters to a few hundred kilometers. And they have, it's just a very good kind of data set where you have very good temporal resolution as well as spatial resolution. And the main statistical metric I will look at today is the second order structure functions. Alexa introduced them yesterday already, and it doesn't hurt to repeat. So the definition is the following. Suppose at a certain snapshot, we have 4 drifters denoted by these 4 red dots. Then the first thing to do is to find all the possible pairs from these 4 drifters. And then for each pair, so for example, if we look at this pair of drifters, we can look at their separation vector, which is just the vector that's connecting the locations of these 2 drifters. And this is my notation for the separation vector. It's in the polar coordinate. It has distance and an angle. So the angle is just the polar angle of the separation vector. And you can also decompose the velocity difference from these 2 drifters. So like this drifter measures a velocity, this drifter measures another one, and you subtract them to get delta U. And you project the delta U vector onto the direction that's along the separation vector and another direction that's across the separation vector. And then the second order structural functions are defined by assuming horizontal homogeneity and temporal stationarity, which means that when you do a statistical, when you do an ensemble average over all the velocity difference at fixed separation, at the fixed separation vectors, the average quantity is assumed to not be a function of time, and it's also assumed not to be a function of the starting location of the drifters. It's only a function of the separation between these 2. And this is what we call the second order structural functions. And on the slides, I will call them SF2s. And more specifically, like the LL means it's the average of the longitudinal component velocity difference squared, and DTT is the transversal component squared. So far I'm defining them in 2-dimensional separation vector space. Again, to repeat the assumptions that have been made so far, we have simply assumed that the average quantity is not a function of the starting location and not a function of time. So just horizontal homogeneity and stationarity. However, in practice, for surface drifter data sets, there is not enough data to compute all the ensemble averages in the two-dimensional separation vector space. So in practice, it's very common to assume another thing, which is assuming that the horizontal statistics is not just homogeneous, it's also isotropic. So like a lot of in a lot of other works, they just do an ensemble average over the same separation distances. So in this work, we do a slightly nicer treatment on this problem. So we follow a framework that's proposed by Wang and Buehler 2021. So Wang is me, and Buehler is my PhD supervisor. So we had a stint with second-order structural functions before, where we are saying that you don't need to assume horizontal isotropy. You can just do a Fourier series in the angles. And then you can say that maybe you don't have enough data to compute all the angular components in the expansion. You may only have enough data to evaluate the ones at the first ends, so only the first angular modes. And so in this talk, I will focus on discussing the angularly independent modes, which means I'm only looking at the first term in this expansion. So this is related to two-dimensional structure functions through a simple angular average. So the data we need is exactly the same, but we are claiming that we are not assuming as isotropy, but we are only looking at the angularly average modes in my talk. And in the paper, we look at the other modes. And also, I will be slightly sloping my notations. So I will drop the superscript C naught here, which means this is the angularly average mode. So from now on, when I write like a second-order structure function as a function of separation distance only, I mean that I'm looking at the angularly average mode. And yeah, so this will be my notation from now on. If this is the first time you hear about second-order structure function, you may wonder what does it mean dynamically. So this is the cleanest way I can see to explain to you what does it mean dynamically. So you can see that this is an average over like things that are separated by some distance. So it's actually conceptually very similar to the definition of covariance functions. And it is just a covariance function shifted by the variance. And then because it's related to the spatial covariance functions, it's also related to the wave number power spectrum of velocities. So then you can work out the relation between the second-order structure function and the kinetic energy power spectrum. So this EK here, I define the EK as the kind of power spectral density per wave number. So if you integrate EK over all K, you get the kinetic energy that's average over the domain. So the relation between the second-order structure function and the kinetic energy spectrum, the exact relation is like this, where this is some kernel that involves the Bessel function. But if you use the asymptotic properties of the Bessel function, you can split this into two contributions. So the first contribution looks like this, and the second contribution looks like this. So the second contribution you can see is integrating from some starting point to infinity, and and in integrand it's the kinetic energy. And here this is in the integrand is kinetic energy times by k squared. So that is roughly the entropy. So the second-order structure function, you can understand that as roughly a combination of the small scale entropy and large-scale kinetic energy is kind of all blurred together. And the weighting between these two terms is affected by the separation distance. And it's not a very clean statistics. And the reason why we still look at them for surface drifters is because the data is irregularly sampled. So it's very inconvenient to compute power spectra directly. We have to compute this kind of pair-based statistics. And so up to this point, I want to remind you again that the surface drifter data have very fine temporal resolution in our case. So the temporal sampling rate is about at least every 15 minutes. That's the data product we use. So you can see the internal wave impacts very well in this data. And however, if you look at the definition of second-order structure functions, since we average over all the time, we so far are not using any temporal information yet. And this is like maybe one of the motivational perspectives we have about this project, which is we want to use the second order structure function, but we also want to use the fact that somehow the data has temporal information in them. Okay, this is talking about the same thing. This is looking at the frequency spectra, and it looks like what you expect for typical oceanic flows. It has slow motions and it has fast motions. And the fast motions here, they peak at the inertial frequency. There are not much tides here, like the tidal peak is very weak. It's also expected because this is a basin and the internal tides shouldn't be very strong there. So the way we propose to use the temporal information somehow is to simply apply a frequency filter and recompute the second order structure functions before and after the filtering. There are some intricate technicalities as we realize very soon. So first, I want to mention that when you apply a temporal frequency filter to a drifter observation, that is exactly the same as what people mean when they say they do Lagrangian filtering. And this is because our drifters, they are approximated to be Lagrangian tracers. They follow the horizontal flows. I think this is related to a lot of people's talk this week, like Manita's talk, myself's talk, and Oji's talk about flow decomposition. And they use a different approach to decompose waves and balance flows. They use like nonlinear eigenmodes or optimal balance. But there is also a very popular approach that's used by many people too, and this is called the Lagrangian filtering. And when they do that in models, they adapt passive tracers in the models, and then they do frequency filters following the tracers. And here we don't need to adapt any tracers. It's numerically very trivial because the observations are Lagrangian time series already. And when you look at why people say Lagrangian filtering is a good way to separate balanced flows and waves, they will say the following thing, which is if you do a simple Eulerian filtering, you will get the Doppler shift effect. And here I want to just formulate state again. What does that mean? So this is already mentioned by Michael in his talks. So the main idea is that if you split the total velocities into the mean velocity and the perturbation velocity, which you regard as waves, and then you just try to derive the dispersion relationship from the momentum equations again, you will get a Doppler shift that looks like this. And the important thing I want to point out here is that this Doppler shift velocity is the mean velocity. It's not your total velocity. It's the velocity after time averaging. And because this Doppler shift velocity is the mean velocity, we believe that if you want to filter waves and balance flows cleanly, the best approach is to follow the frame that's following the mean velocities, and this is this is also consistent with the generalized Lagrangian mean framework is introducing this nice book. I think even without considering the intricacies of the GLM framework, I think I'm pretty convinced up to at this point that even if you just want to filter waves and the mean flows, it's better to follow the frame that's moving with the velocities of the mean flow. And this is a sketch from the textbook on what maybe more exactly what do you mean. So here we have a idealized particle that has this kind of movement. So it has a fast oscillation and a slow movement. And so you can low pass filter the displacement to get a mean trajectory that looks like this, which automatically filters out the displacements that are induced by the fast movements. And the GLM framework is just saying that when you do Lagrangian filtering, you should follow the mean trajectory, and then you can attribute your filtered velocities. So both the low pass and high pass filtered velocities are attributed to the locations at the same time on the mean trajectory. So this is what we mean more exactly. And if you are into this kind of stuff, you can also see that there is another very popular, there's a very popular Lagrangian filtering package, which follows a different framework that we refer to as the particle trajectory framework. So this is also Lagrangian filtering, but instead of following the mean trajectories, they follow the actual trajectories. And this is currently applied in a lot of very nice packages, very nice and very popular packages, like the one by Shakespeare et al. But they, again, I think they are doing a less clean job than the GLM frame because they are following the particle trajectories instead of the mean trajectories. And again, to repeat my argument for the GLM approach, my main argument is that the Doppler shift term is induced by the mean velocity. So if you want to cancel the Doppler shift term, you should move with the mean velocity. And another argument I would make is that if you think about this kind of sketch, and so for example, you want to extract the mean flow, then if you follow the particle trajectory instead of the mean trajectory, then you are moving like your own movement has a fast component in it. So this would mean that you are not experiencing the mean flow at the purest form. Like if you want to really be a mean flow, you have to follow the mean trajectory. And this is related to the point. It's made by a nice work by a group in Edinburgh, and they are comparing the particle trajectory versus the mean trajectory framework. So the first panel is the raw vorticity, and the second panel, this is the Lagrangian filtered mean vorticity, but following the particle trajectory frame. And the third panel is the Lagrangian filtered mean vorticity that's following the mean trajectory frame. This is buried in the appendix, but I think this is a very powerful illustration that at least in this kind of idealized extreme cases where they make the waves very strong, you can see the effect and you can see the benefit of following the GLM mean trajectory frame when you filter the waves. Okay, so we just repeat that thing for every single drifter recording. So this is just showing you what we do exactly for the drifters. So I will take one drifter trajectory as an example. It's highlighted here in blue. This is how the raw trajectory looks like. And this is how the frequency spectrum of the velocity looks like from this one trajectory. And again, you'll see the peaks around the waves. And the frequency filter we apply is set such that the high frequency component contains like everything around F and everything higher than F. And the low pass component is cut off before the initial peak. So we apply this, so then we see the effect of this on the trajectory immediately. So before the filtering, you see these initial oscillations in the blue line, and after we apply the low pass, it's all filtered out. And the yellow line, the low pass trajectory, is the frame that we will use when we compute the second-order structural functions again. And we also filter the velocities, and they look like this. So we repeat this for all the drifter recordings, and then we compute the filtered second-order structural functions. So they are defined like this. So first we filter all the trajectories. So we move from this panel to this panel. So these are the trajectories of two drifters, and these are how they look like when both trajectories are low-pass filtered. And so let's look at the current points denoted by the two dots. So those are the locations of the mean trajectories at the same snapshot. And then we compute the separation vector based on the mean trajectories. So we denote this as RS, where S means slope. And the low-pass second-order structure function is defined as the ensemble average of the difference of the low-pass velocities as a function of the low-pass separation vectors. And the high-pass second-order structure function is still defined on the low-pass separation vector because we are still looking at the mean trajectory frame, but the velocities are replaced by the high-pass velocities. So we do this to the GLAD and laser data, and this is the wave mean decomposition we get for second-order structure functions. So we see that in both cases, we seem to get results that make sense. The low-pass motions dominate at larger scales, and high-pass motions dominate at small scales. So this kind of agree with the textbook kind of paradigm where waves should be at smaller scales and balance flow should be at larger scales. And we also do a Helmholtz decomposition of second-order structure functions. So what we mean exactly is that the horizontal velocities can be decomposed into a component that's purely divergent and another component that's purely rotational. And I will skip this next part. So the main reason why people do a Helmholtz decomposition is that it's a very nice heuristics into the dynamical regimes you are in, because different dynamical regimes leave different imprints on the rotational versus divergent component. So I will skip through this, and I want to mention that if you look at the Helmholtz decomposition formula, it doesn't look like it's something that can be applied to surface drifters because they have horizontal derivatives in both directions, and your data is not regularly based enough for you to evaluate all these derivatives directly. However, there is a smart mathematical trick to at least decompose the contributions from the rotational and divergent components of the velocities into the second-order structure functions. So this can be done at the level of second-order structure functions, although not at the level of individual snapshots. This was first derived for power spectra by Buehler, Callis, and Ferrari, and then Lindbergh change it into the second-order structure function version. It's actually like he's just using the relations between second-order structure function and power spectra. I also want to mention that, so I'm still looking at the angularly average second-order structure functions. And in Wang and Buehler 2021, we showed that when you have anisotropic statistics, the angularly average formula for the Helmholtz decomposition doesn't change, it looks the same. And then Lindbergh got back to us in 2025. He relaxed some other assumptions we made about the cross spectrum in 2021 work. So basically, it's the same formula, but the assumptions involved are keeping relaxed. So now for this formula to work, you just need horizontal homogeneity and temporal stationarity. You don't need anything else. So we apply the Helmholtz decomposition to the second-order structure functions. So first is that if we apply that to the unfiltered second-order structure function, which is in the second line, you can see that the rotational second-order structure function is dominating at large scales, but at smaller scales, there seems to be a disagreement between laser and GLAD. And also, if you compare the Helmholtz decomposition with the actual wave mean decomposition that's computed by Lagrangian-filtering in the first row, you can see that the Helmholtz decomposition can be pretty misleading at small separations, especially in the laser data, where it says it's mostly rotational, but in the wave mean decomposition, you see very strong waves at smaller separations. Okay, I will try to be fast about this. And we also do this for the high pass and low pass filtered second-order structure functions separately. For the high pass second-order structure functions, we see something very nice, which is that the divergent second-order structure function in the high pass component is always larger than or equal to the rotational second-order structure function. And this agrees very well with linear internal wave series, which is saying that if you just rearrange the horizontal momentum equations, you can derive that the ratio between the stream and potential functions, or like a vorticity and divergence, it should be roughly proportional to the ratio between the Coriolis frequency and the intrinsic frequency of the waves. So then, because propagating internal waves have omega larger than f, larger than or equal to f, you would arrive at the conclusion that the divergent waves should be always larger than or equal to the rotational waves, at least following the linear models. So another interesting thing we see is that at larger separations, the divergent and rotational second-order structure functions start to be very close to each other. So this is maybe more clear in the GLAD data. In the laser data, they are kind of comparable across all the scales. So what does it mean if you think about this simple relation between vorticity and divergence for waves? It means that the frequency, the waves that are imprinting these second-order structure functions should have frequency that's very close to f. So I think this is an indirect evidence of the imprint of near inertial waves. And I think it's very nice that in the GLAD data, we see this to happen at large spatial scales. So this also agrees with the simplistic expectations for near inertial waves. So the laser data looks interesting because it looks kind of near inertial wave-ish across all scales. So we have some speculations, maybe there's some mechanism that's trying to move the near inertial waves into small scales. So as a reminder, the laser is in winter and the GLAD on the left panel is in summer. So maybe in winter, there are more like funk activities or something like that that's generating low frequency internal waves at small scales. Okay, I will skip this, but my point was that if we apply the particle trajectory, then we get very wrong conclusions, and this is because like you should do this in the mean trajectory frame. And I will skip over the part one because I have a part two also. So the summary of part one is that we propose to apply frequency filters to surface drift observations along the mean trajectories. And we learned some lessons on flow decomposition. So first, composed decomposition can only give you some good heuristics at large spatial scales. And also, if you do Lagrangian-filtering, you should try to follow the mean trajectory instead of the particle trajectories. And the Helmholtz decomposition of the high-pass structure functions agree with linear wave series, and in winter there seems to be more small-scale near inertial waves. So for part two, I will try to do it in 3 minutes. So part two is a collaboration I started in January with these people, and Han Wang is the one who did most of the work. So the thought process is the following. So far we have only looked at second-order structure functions, but the same framework can be applied to all the other drift statistics we know. So one other statistics in particular that we're interested in is the third-order structure functions, from which we can diagnose cross-scale kinetic energy transfer. And this is something Alexa mentioned yesterday too. And so our idea is that maybe we can compute third-order structure function from the low-pass component in drifters that overlap with SWOT satellite observations, and we can compare how well it agrees with the SWOT geostrophic velocity products. And we found a data set where like there are about 100 drifters that overlap with the SWOT cover track, and we carefully pick the SWOT observations that's on top of the circuit drifter trajectories, and we compute the structure functions. And so these are the structure functions from the drifters. And this is just repeating what we did with the Gulf of Mexico. We had some similar conclusions, except that we also find that for the low-pass component, in this area, the rotational component absolutely dominates over the divergent component in the low-pass motions. So this gives us some confidence for going ahead and compare with the geostrophic velocities from SWOT. And this is the third-order structure function we computed. Maybe we can focus on on panel C, maybe that's the gas panel. That is the inferred cross-scale energy transfer rate that's inferred from the third order structure functions. And the magenta line is from the unfiltered drifter observations, and the red line is from the low-pass filtered drifter observations, and the blue line is from the SWOT geostrophic velocities. So what is interesting is that the sign of the energy transfer agree pretty well, and it's mostly upscale energy cascade, and only starting to be downscale at the largest wave numbers. But the magnitude of the energy transfer diagnosis is much bigger from the drifter data than the SWOT data. So currently, we think maybe we should weigh the SWOT observations in a more careful way so that they agree with the drifters better. So this is where we are currently.
Thank you very much.